All right, in chapter 17, and really the thing that you need to take away from chapter 17, I know there's a bunch of side chain reactions and stuff. That is not nearly as important as being able to recognize which molecules are aromatic and which molecules are anti-aromatic. Okay, so again, just a quick definition. An aromatic molecule is a molecule that is much more stable than Lewis theory would predict. Okay, Lewis theory is this line structure. You learned it in Gen Chem, maybe in high school, but it doesn't take molecular orbital theory into account at all. Aromaticity derives from molecular orbital theory. Well, sorry, I guess molecular orbital theory explains aromaticity. There are some molecules that just are way more stable than Lewis structure would predict. There are some molecules that are much less stable than Lewis structure would predict, and we call those anti-aromatic. Okay, anti-aromatic molecules essentially don't form. Either you can't make them at all, like cyclobutadiene, or like cyclooctatetraene. If you can, they'll pucker out of planarity, and now if none of the p orbitals are conjugated, it's not anti-aromatic, it's non-aromatic. Most molecules are non-aromatic. They're neither much more stable nor much less stable. So the program here is, the question here is, I want you to circle the aromatic molecules in this list, and I want you to put an X through the anti-aromatic molecules. If a molecule is non-aromatic, don't say anything. Okay? So hit pause and do that and come back. Okay, now that you've done that, I'm going to go ahead and circle the aromatic molecules. And I'm going to put a red X through the anti-aromatic molecules. And now we can go through, if you got that, you probably have it. If you didn't get it, I'm going to walk through how this works. First of all, you should probably memorize some things. A benzene is aromatic, and if a molecule has a benzene in it, the molecule is aromatic. So we have, if you look at Huckel's rule, you got to have a cyclic set of conjugated p orbitals. To have them be conjugated requires planarity, right? If you think about conjugation, all these p orbitals have to line up. If we have a p orbital, right, that's orthogonal, these two p orbitals, even though they're next to each other, they're not coplanar, so they can't overlap. So to have a cyclic set of conjugated p orbitals requires that the molecule be planar. And then two, for aromaticity, there have to be 4n plus 2 pi electrons, and n is an integer. Okay? So again, don't try to imagine don't go into it thinking what n is, just count. So in a benzene, you've got a cyclic set. It's uninterrupted. There's a p there, sp2, 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 and you're back around. And there are 2, 4, 6 electrons. So 6 pi electrons, this is 4 times 1 plus 2, right? That's aromatic. It's coplanar, all those p orbitals are conjugated. So like I said, benzene molecules, benzene structures are aromatic always. I've said here, the second one is non-aromatic. It's not anti-aromatic, it's not aromatic, and why is that? And the reason it's neither, it fails criteria 1. Right? We don't have a cyclic set of p orbitals. So it's a 6-membered ring. You got an sp2, right? sp2, 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 but sp3, sp3. Neither of these two atoms have a p orbital. So that's non-aromatic. It's your Lewis theory will explain it pretty well. I've said the third one, the cyclopentadienyl cation, is anti-aromatic. Remember, if there's an anion here, it's aromatic. I did that in the PowerPoint show. So what's going on here? Well, we meet criteria 1. sp2, so there's a p orbital there. sp2, 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 sp2. So there's a cyclic set of p orbitals. So criteria 1 is met for this third compound. Criteria 2, for an anti-aromatic molecule, 4n pi electrons. All right, again, where n is an integer. Well, how many electrons do we have in this structure? 0 from the cation. Remember, a carbocation is a carbon that's got it's sp2 hybridized, so it's got a p orbital, but has no electrons in that orbital. 2, 4. So 4 pi electrons. That means this is anti-aromatic. Right? It's pretty simple once you get the hang of it. It's getting the hang of it that's important. So cyclic set, that's the first test, and then counting the electrons. And that's where people always try to make this a lot more complicated than it is. You're just counting how many electrons are there. You're not trying to imagine some number it's got to be. Just count what's actually there. So I've said the fourth one, cyclopropenyl cation. And look, if you look at that structure without thinking about molecular orbital theory, you should say that is really unstable, right? It's a 3-membered ring. All 3 carbons are sp2 hybridized, so they want to have a bond angle of 120. Instead, they have a bond angle of 60 because of geometry. And there's a carbocation, a secondary carbocation. That looks like a terribly unstable molecule. And you'd say, you might say, I would have said, before I became an organic chemist, that can't be formed. In fact, it's quite stable. You can make it. It's obviously going to react with nucleophiles. Nucleophiles will attack the carbocation, but you can make it. And if there are no nucleophiles in the solution with it, it will just sit there. It's aromatic. So how do we get that? sp2, sp2, sp2. So that's a cyclic set of p orbitals. There's only 3 of them. It's got to be coplanar. 3 points define a plane. So those 3 points, those 3 atoms have to be coplanar. And how many electrons now? 0 from the carbocation, 2 from the pi bond. And so this is 2 pi electrons, and that's equal to 4 times 0 plus 2. Integer. 0, 1, 2, 7. Okay? So 2 pi electrons is an aromatic molecule. The next one I've said is non-aromatic. It's the same reason as this one. And that's actually going to be the reason most molecules are non-aromatic. Right? So sp3 right there. You only have to find one sp3 in the ring. Okay? So that's an sp3 as well. Actually, in this case, that is also got a lot of sp3 character. But you only have to find one. So to know that we don't have an uninterrupted cyclic set of p orbitals. So this is non-aromatic. Okay, the last 2 might have thrown you a little bit. Got 2 lone pairs on this oxygen. Coming down here, we have 1 lone pair. Well, what's going on? So sp2, 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 sp2. So that's 4 in a row that have a p orbital. This oxygen, normally you would look at an oxygen with 2 lone pairs and 2 covalent bonds, 2 sigma bonds, and say that's sp3. But again, hybridization is an estimate. It's a hybridization itself is kind of an approximation of molecular orbital theory. If this oxygen adopts an sp2 configuration, then look what happens. So let's say that's sp2. Put a lone pair there, and a lone pair there, and then back to here. So if we have p orbital here, p orbital there, p orbital there, right here are. So if each one of these sp2 carbons, their p orbitals can line up with the oxygen, pi bond, but now one of the lone pairs, one and only one of the lone pairs, right? The other lone pair is going to stick out there. You can't put 2 lone pairs in exactly the same place on the map. So this lone pair can line up with the pi system, and now look how many electrons you have. You have 2, 3, 4, 5, 6 pi electrons. You have a cyclic set of p orbitals, and so this is 6 pi electrons. This is aromatic. All right, so really, another structure you can sort of memorize if you want. Any 5-membered ring with 2 double bonds and an atom here that has a lone pair is going to be aromatic. Right? That could be a carbon, and then that lone pair makes the carbon negative. That could be an oxygen, a nitrogen, a sulfur, a phosphorus. There's a whole lot of atoms that would fit there. Well, then what about the molecule on the very end. You've got a lone pair there. There's a positive charge. So how is that aromatic? Well, by going to a 6-membered ring, now we have 2, 4, 6. This oxygen, if we look at that, right, the oxygen is sp2. That's obviously an sp2 oxygen because it's in a double bond. Well, you have one electron in the p orbital that makes this pi bond. That means the lone pair then have to be out in front. And so this oxygen can only contribute 1. You got 2, 4, 6. That's 6 pi electrons. You've got a cyclic set of p orbitals, so that molecule is aromatic as well. There's a rule here that basically no atom in the ring can contribute more than 2 electrons. Every atom can contribute 1 p orbital, right? If this p orbital lines up with the rest of the pi system, there can't be another p orbital on that atom in the same place, right? P orbitals are all orthogonal to each other. And so that, I put a third dot there, this orbital can have up to 2 electrons. So the p orbital on that atom that's contributing to the pi system can have 0 if it's a cation, 1 if it's neutral, or 2 if it's an anion, or a lone pair. So each atom can contribute up to 2 electrons. Then the second lone pair on an oxygen is going to be out in front. If that's a nitrogen, that's a bond. If it's a sulfur, it's a lone pair. But you get the idea. All right, you're going to see a lot of those. I can almost promise that one of those will be on the exam.